right, so in this video, it's going to be split into two parts, but basically right now, as I'm doing this, I'm going to do 6.3 and 6.4 together, solving basic trig equations, and then solving general trig equations and applications. So really a key to both of these is that you have to first isolate a trig function, kind of like when we're solving absolute values. You first have to isolate the absolute value. That's also going to be true about the trig function. You have to isolate the trig function by using algebra. And then you might also have to use some trig identities if there's more than one trig function. So, because it always has to be written to be able to solve them, it always has to be written in either in factored form with multiple trig functions. So what I'm referring to there is something like I could do sine of x minus 1 cosine of x plus 2/3 and something like tangent of x minus 2. I could do something like that, but it would have to be equal to 0, and so I could use the zero product property. But most of the time, if I have all of these without the parentheses, so it's not written in factored form, it's not being multiplied, and they're just being added or subtracted, I can't solve that until I'm able to rewrite it into factored form like this, or where there's only one trig function. So that's where the trig identities are still also going to play an important role. And then the second step to this is once we get it down to factored form or to one trig function, we can then use the inverse trig to be able to solve for the angle. So remember, when you're solving and you're using inverse trig, you are finding the angle and you're taking the inverse trig of a length. Okay, so just to kind of reiterate that, remember, when you are taking the inverse trig of something, you are taking the inverse trig of the side length and you are finding the angle, okay? Or we could say right here, to find the angle. Okay, so that's another way of looking at it. All right, so let's go ahead and move on. Now here's another example. So again, we want to look at this to see if we can determine what the equation is and what we're trying to solve, and then identify primary, secondary, and principal not primary, principal root, secondary root, and then all real roots. So first, looking at this graph, this is a good review for chapter 4 of being able to find the equation of a graph. We've got a maximum of, let's see, this would be, because it looks like every line is counting by 0.5, so this would be a maximum of 11. 11 min of 0, which means our k value is at 11 divided by 2, or 5.5. So let's see. That's our k value. Okay, then we can see that our amplitude is going to be equal to also 11 divided by 2, which is 5.5. And then finally we can see that in terms of the y-intercept, it starts at the minimum. So this is going to be negative cosine. And it repeats itself within pi. So that means our b value is 2 pi divided by pi, or 2. So finally, our equation here is negative 5.5 cosine of 2t plus 5.5, and it is equal to our b value right here, which appears to be 8.485. All right, so we want to go, if we're doing this by hand, we want to solve for cosine first. So we're going to subtract 5.5. So we get negative 5.5 cosine of 2t is equal to 2 2.958, and then we're going to divide by negative 5.5, and so we get cosine of 2t is equal to negative 0.5378. And then we would do inverse cosine, so 2t is equal to inverse cosine of negative 0.5378. Then we would divide that by 2, and we would get our primary value. So that's how we would do it algebraically, but again, we can look at the graph here to get a pretty good idea of what that's going to be, because again, in this case, we're looking at our angles from 0 to 2 pi and 0 to pi. So first of all, looking at it from 0 to pi, you can see that we actually have two principal roots on this one. We have a principal root in the first quadrant, and we have a principal root in the second quadrant. That's because our b value of our angular frequency, because our angular frequency is 2, that means we're going to have two principal roots, and then we're going to have twice that of our secondary roots or solutions from 0 to 2 pi. Okay, so if we go ahead and write these out just how they're written, we can see that our principal roots, according to our graph, are equal to pi thirds and 2 pi thirds. Okay, now if you guys think about this in terms of the quadrant in the unit circle, we have pi thirds here, and then we have its reflected angle across the y-axis at 2 pi thirds. So when you plug this into your calculator and you go through and you solve it, if we're not going to get it into exact form, which is what the graph is nice for in this case. So if we go inverse cosine of negative 0.5378 divided by 2, we get the answer of 1.069. This answer over here is actually going to be pi minus 1.069. Which is going to give us 2.0723. And so that's what basically, if you do pi thirds and 2 pi thirds, you're going to get approximately those two decimal values. Now we know within 2 pi, because this was a double angle, we ended up with two more values that are also going to work for this. We have this one right here that is in the third quadrant, and then we have this one right here, which is in the fourth quadrant. If you look at it, basically it is from first principal root to its reflective is a distance of pi, which is the period. And then here from the second principal root to its reflection, we also have a distance of pi, which is equal to the period. Okay, so all possible solutions from 0 to 2 pi are all of our primary roots and secondary roots. There's our primary, and then our secondary is the 4 pi thirds, which is basically pi thirds plus pi. And then our secondary is 2 pi thirds plus pi, which is basically just 5 pi thirds. Okay, and then finally what we can see is that basically all of these are just adding 2 pi to it, but because the period is pi, we can also write our all real solutions as pi thirds plus k pi and 2 pi thirds plus k pi, and that would actually take care of all of these just through the entire number line. So this problem, we're supposed to find the principal root and the solution from 0 to 2 pi. We're not going to do all real solutions because of the complicatedness of this function. So then from this point, remember what we do is to be able to do the inverse of secant, we actually do the inverse of cosine and then take the reciprocal of 8. So then on the second one, we get x is equal to inverse secant of -2, which inputted into our calculator has to be inverse cosine of the reciprocal of -2, which is -1/2. So when we plug these in, we get the answer of, let's see, inverse cosine of 1/8 gives us the answer of 1.445. And then inverse cosine of -1/2, that's on our unit circle. It's at -1/2 at 2 pi thirds. So those would be our two principal roots. So now how do we find the other roots? So what we want to consider is the quadrants that these are in. So if we picture this graphed out, these are two totally different angles. So we know that 2 pi thirds is in the second quadrant, and then its reflective angle is the 4 pi thirds in the third quadrant. So this is 2 pi thirds, and this is 4 pi thirds. Okay, and then these two places represent the two places where cosine would equal -1/2. So now we have the 1.4485, which would be the two places where cosine is equal to 1/8. Those would both be in the first and fourth quadrant instead. So again, in this case, to be able to find the fourth quadrant one, we're going to have to do 2 pi minus 1.445. And so that would give us our second answer when we do that. And so that's how we find all the solutions within 0 to 2 pi. All right, again on this one, because of the complicatedness, if it was just a single trig function, we would look at all real solutions. But since there's more involved here, we're going to go ahead and write this where it's just going to be the principal root or roots and then solutions from 0 to 2 pi. So first of all, this is factored, but it's not equal to 0. So what we actually have to do is multiply this out, and then we're going to subtract the 1, get it equal to 0, and then hopefully be able to factor it again. So remember, when you're multiplying binomials out, you have to when it's squared, you have to multiply it by itself. So some of you may remember it as foiling, some may have done it with an area model, some just do the distributive property. But basically remember, you have to multiply every term in the first function by every term in the second function. So we get cosine squared of theta plus cosine theta sine theta plus cosine theta sine theta again plus sine squared of theta. Okay, so then we know this simplifies to cosine squared plus sine squared plus 2 cosine of theta times sine of theta. So then we know that this equals 1. So we can write this as 1 plus 2 sine of theta times cosine of theta. Sorry, I'm such in the habit of writing sine first, so that's what happened there. And then we can subtract 1 from both sides, so we get 2 sine of theta times cosine of theta is equal to 0. Divide by 2, so we get sine of theta times cosine of theta is equal to 0. This is in factored form, so we can split it up with 0 product property. So sine of theta is equal to 0 and cosine of theta is equal to 0. And then we actually know sine, remember, is between negative pi halves and pi halves. And it is equal to 0 at the value of 0. And then cosine is between 0 and pi, and we know that it is equal to 0 at pi halves. So here's our two theta values for our principal roots. And then to be able to find our solutions, we just need to say within the unit circle where else does sine and cosine equal 0. So we know the other place where sine is equal to 0 is at pi, and the other place where cosine is equal to 0 is at 3 pi halves. And so there's our answer for our principal roots and then the solution from 0 to 2 pi.